For the actuator test, what you can see mechanically happening is the turning on and off of the motors and solenoids in 1 second intervals. So as you can see at the start, the motors start spinning for 1 second, then turn off, as well as the solenoids being activated for 1 second and then turning off for 1 second. And you can also, if you listen closely, you can hear the clicks in the pneumatic valves, which shows also a turning on and off every second.
In this code, the loop basically starts all of the valves, solenoids, and motors at 0, so all of them are off currently. And then it waits a second, and then it turns all of the valves, solenoids, and motors on, and then it'll wait a second, and then the last line basically just repeats it so that it changes direction once again, and continues with the loop. Every second it changes.
As can be seen in the Arduino test, the speed of one motor is determined by how close something is to the IR sensor, while the other is determined by the potentiometer, which can either increase the speed from 0 all the way to its max 255. Then as can be seen, the switches have different effects on the different actuators assembled to the Arduino, including the solenoids and also the valves in this case. So within the Arduino test code, we see that most importantly we have 4 buttons being red and their states always being red, as well as an IR sensor, a potentiometer, encoder direction, and the speed of the motors being set based on what the IR sensor is giving out and also what the potentiometer is giving out. One motor is determined its speed by the potentiometer, the IR sensor, and the other motor is determined by the potentiometer, as can be seen in the video. Now, for different configurations of the buttons, different actuators are actuated. In our case, unfortunately, the polarities were reversed, so 0 unfortunately means on, while 1 means on. So for example, when this button is pressed, all are turned off. And when button 4 is pressed, all are turned off. Are turned on, my bad. And in button 3, pin 1 and pin 3 are turned off, pin 2 and pin 4 are turned on. After time has run out, which is determined by the millis counter, everything is shut off in the program, and in order to restart the program, the Arduino must be restarted.
As you can see, when the button is pressed, the solenoid pulls the metal rod in, and when the button is pressed again, it releases the metal rod. In the code, in our void loop, we read the button state in the 11th line, and in the if statement, for our code, our polarities are reversed for the button. So in this case, 0 is going to mean on, 1 is going to mean off. So when button state equals 0, so when button state is clicked and current state is off, that means that the current state is going to turn on. So the motor is going to start running. And we used a delay of 50 because it worked in this case, just fairly reasonably. If else, the button state, when it's turned on, and the current state is already on, it's going to turn the entire motor off. Same with the delay here. And if the current state is on, the light turns on, and if it's off, then the light is going to stay off.
So from the first video, we can see as we turn the encoder, the motor slowly starts getting faster and faster, with 10% each time the encoder detects 18 different clicks. The second part of this video shows that with the 2 buttons, one button spins the motor clockwise and the other button spins the motor counterclockwise, which can be indicated also by the green and red LEDs on the Arduino itself, one indicating clockwise and one indicating counterclockwise, related to which button is being pressed. So as can be seen here, we have button 1 and button 2 that is constantly being read by the Arduino with their respective pin numbers. Then we have the encoder count, which reads how many times the encoder has been spun and does some manipulation to the number, which we'll explain later. Then we have the different cases for the buttons. So if both buttons are the same state, so either pressed or unpressed, then neither of the LEDs will be lit and the speed of the motor will be 0. Then if button 2 is pressed, the motor will spin clockwise and the speed will be set to the speed that the encoder sets, which is labeled here as P speed. And one LED will light up. If the other button is pressed, it will spin counterclockwise. The speed will be set to the classic speed that the encoder sets, and the other LED will be lit up. Now, if the encoder reaches 18 clicks, and the percentage is not yet at 100, so basically if the motor is not at full speed, we reset the variable encoder count to 0, and add 1 to a counter. And then to our percentage, we add 10%, setting the speed at that percentage times 255. So for example, if we're at 10%, the speed will be 25.5. Now, we mentioned here, we also account for negative, so in the other direction of the encoder. Now, we see the count here, and the count is important because the robot encoder count, this variable, or this reading, will always keep going up. But we have to be able to reset this number each time it gets to 18. So the way we do that, for example, if we reach the number 18 the first time, the count will be 1, and it'll essentially be 18 minus 2 minus 1. Because here we say it's count plus 1, so once it reaches 18 the first time, count will be number 2, and minus 1, so 1 times 18. So 18 minus 18. If we're at 36 clicks, count will be 3 minus 1, so 2 times 18, 0. So essentially this will always be within a range of 0 to 18. And yeah, we also put a debalancing delay, and this is where we remove the motor. Essentially the speed can either be P speed set by the encoder or 0 set by both buttons being pressed at the same time.
As you can see, when an object comes into 6 to 10 centimeters of the IR sensor, the motor begins to rotate for 10 seconds, and when the banana plugs are put together, the motor stops. As we can see in this code, in our void loop, we determine the distance by getting a ruler and determining 6 to 7 centimeters, and recording the output. And using the output, we were able to determine an equation that could convert the output into centimeters. And we can see in the next if statement that if the distance is between 6 to 10 centimeters, the timer begins and the motor will start. And the timer is equal to what the millis were at that exact time. So then in the while statement, right after that, it basically says that while the motor's been running, how long it's been running, if it's under 10 seconds, and the banana plugs have not been touched together yet, then the motor's going to keep going, basically, and the button is going to keep being red to see if the banana plugs ever get touched together. And so the motor's going to keep running, and once the banana plugs are touched together, the loop stops, and it goes to robot.moveMotor, and it turns off, in this case, which is basically making the banana plugs the kill switch in this scenario.
As can be seen in the video, we are now using an ultrasonic sensor instead of an infrared sensor. And both at 6 centimeters but also at 10 centimeters, the sensor gives a very accurate reading as compared to the infrared sensor. Most especially, the infrared sensor, while it was and could be unstable from time to time, the ultrasonic sensor is much more stable and the readings are much more accurate, especially without any calibration. Problem 5 is very simple, as all we have to do is read the distance of the ultrasonic sensor right here, and then print it out. What we've noticed with the ultrasonic sensor is that it did not need any tuning or any calibration as compared to the infrared sensor, and it also did not need any. It was also much more stable than the infrared sensor, as the infrared sensor could sometimes give us accurate readings, but other times it wouldn't. This is largely believed due to interference and the infrared sensors being more susceptible to interference, while the ultrasonic sensors are less susceptible to interference.